In this quick video, we're going to be going through equivalent statements from Proof 411 Specialist Maths. And first of all, let's have a look at the following statement. If a triangle has side length of A, B, and C, then we know that A squared plus B squared is C squared. But it's if and only if the triangle is a right angle. So the clause if and only if means that there are two statements. We can basically say that if A squared plus B squared is equal to C squared, then we can say that it goes both ways. It says that the triangle is right angled. But likewise, it also, so this implies that it is right angled, but likewise, we also go the other way. If the triangle is right angled, then it also implies that A squared plus B squared is equal to C squared. Now, what if we have it that it goes both ways? It's what we call, so we can say that this is what we call the converse of the other statement. If I call this P and I call this Q, we can say that P implies Q, and the converse is what? Q implies P. Now, if P implies Q and Q implies P, then we've got this equivalence here, and what we can say is we can actually use what we call a double head arrow. Okay, P implies Q. Also, it basically means that it's if and only if. This is what we mean by if and only if. We can see this double-headed arrow here. Okay, and that means that yeah, P implies Q, but also the converse Q also implies P. So let's consider the statement x squared greater than y squared if and only if x is greater than y. Well, of course, we could then say that we've got our double-headed arrow. And what we've really got to do is we've got to prove both the implication and the converse. So we've got to prove both sides. So there's always, whenever we've got this, we've always got that there's always two proofs. P implies Q, Q implies P, and then once we do that, we can then conclude that they're equivalent. Okay, so if we can prove both ways, so we first of all prove that P implies Q. We then do the same for the converse, and then we can hence conclude that P is if and only if it implies Q. Okay, so let's have a look at this. Now, this one we've done already for you. I'm going to leave that up there, and by all means, you can pause this if you've got your notes in front of you. But let's have a look. It says here, prove that a number n is even. Let me talk you through this. If and only if the number n minus 2 is even. So what you can see is we've got to start and imply, let's say that P implies Q. We've got to prove that first. So we're just going to assume that n is even. And of course, if n is even, then we can say that n is equal to 2k, such that k is some integer. And of course, if I then subtract 2 from both sides, you can see there that 2k, that is also even. So that means that we've just proven that n minus 2 is also even, and that means that we've done the first step. Okay, if n is even, this implies that n minus 2 is even. Likewise, though, we've got to do step 2, don't we? We've got to go from the other way. We're assuming that n minus 2 is even. Let's show that n is even. And as you can see, if I have n minus 2, we know, well, we're assuming that's even. If I then add 2 to both sides, look at that. That happens to also be even. So we've done step 2, P implies Q. Now Q implies P. Therefore, we can deduce that clearly if I've done P implies Q and Q implies P, then we can say that these are equivalent. Okay, we've done it both ways. Okay. Now, I'm going to pause this for a second because I'd like to talk with this class about how to go through and do this one. by all means, if you want to pause the video and go through it, you can do so as well. I'm going to go through this in a second, but you can see if I was to, let me just share this with you. So we can see that we've broken this up. We know that 1000A plus 100B plus 10C plus D is, we're proving that, of course, it's a multiple. A plus B plus C plus D is a multiple of 3. So we've done that. We've done that there. We've broken that up. We've taken out a common factor of 3, and we can see that, well, clearly, if this is a multiple of 3, then this remainder must also be multiple of 3. And likewise going the other way. And of course, once we've proven it, we can say QED. Therefore, it is shown. That was a bit of a unique one, but likewise, what about if we were to do something like this? Well, let's assume, so of course, we've got to say that x squared greater than y squared if and only if x greater than y, and we also know that y is greater than 0. So let's try this one here. First of all, what we can do is we can obviously assume that x squared is greater than y squared, and therefore we can, let's subtract y squared from both sides. We can say that x squared take y squared is greater than 0. And if I go ahead and factorise that, we can go that that's x take y, and x plus y is greater than 0. Now we know that y is greater than 0. We've been told that. So and we also know that that x squared is greater than y squared. So if you wanted to, we could sort of divide both sides by x plus y, and we know that that's going to be positive, and that's also going to be positive. Okay. Likewise, I guess really what we could do is just essentially divide both sides by x plus y, and that gives us x minus y is greater than 0, which means that x is greater than y. So you can see there that we have, if I call this P and I call this Q, then we've just proven that P implies Q, haven't we? Now let's look at the converse. So essentially we've gone one way. Let's go the other way. So we've got if we've got x greater than y, then how do we get to the other side? How do we? I'm asking the class now. How do we get to the other side? What do we do if I want to go the other way and prove the converse? Q implies P. Yeah, we've got an answer in here, and that's, so we've started off with, of course, this. We want to prove that Q implies P, the converse. Well, what we've done is we've started with that, get it on the other side, and now what I'm going to do is I'm going to multiply x minus y by x plus y. I'm going to do the same to both sides. So we're really multiplying by x plus y. But of course, that's going to multiply by 0 is still 0, isn't it? So, and as you can see, that's going to give me x squared minus y squared. If I was to expand, is greater than 0, which means that we can say, therefore, we can say that x squared greater than y squared is if and only if we've just proven equivalence, x is greater than y. So we've done it. Step 1. Step 2, prove the converse. Step 3, we're talking about we've now proven equivalence. So that's really as far as it goes. We're not going to go too much further than that. And really, that's about all I have to say for it. In particular, if I have a look at some of the coursework, if we go ahead and look at some of the coursework, I think wasn't 8E, was it? It was 8D. Just proving, yeah. So quite a few of these. It and again, likewise, you will see a few of these funny ones where which of these pair of statements are equivalent. Vivian is in China. Vivian is in Asia. Well, do they are these equivalent? What? Exactly. Asia doesn't necessarily mean that you're in China, does it? Yeah. So if x equals 2, does that mean that 2x equals 4? Would these be equivalent? Yeah. So you can prove that 2x is 4 and then go the other way. X is equal to 2. So a lot of these, there's a few of these which are worded ones as well. Let n be an integer, prove that n plus 1 is odd, and if and only if. So again, we're looking at proving one way, then proving the converse, and then hence doing our double-headed arrow. So a lot of these are actually, once you get the hang of them, are pretty straightforward. Just applying it both ways and then proving equivalence. All right, I'm going to stop there.